Greetings and salutations, magical chemists. Let's talk about the glories of covalent bonding. Covalent bonding, of course, is when two nonmetal atoms share electrons to fill their valence levels. So this occurs between elements that have similar electronegativities. It's not that they're sharing because they're nice. They're sharing because neither one is strong enough to pull the electrons away altogether. And of course, the smallest group of elements held together by covalent bonds is called a molecule. Atoms can make single, double, or triple covalent bonds depending on if they share 1, 2, or 3 pairs of electrons. Now, not all elements tend to form multiple bonds. Most of the time, you're going to form multiple bonds between things carbon, nitrogen, oxygen, phosphorus, and sulfur. So if you remember synops, like Cyclops, but without the I. Or, well, without the letter Y, although Cyclops has an I. Different story. Okay, so the synops elements will form your double or triple bonds. Properties of covalent bonds include low melting and boiling points because the molecules aren't being held together by covalent bonds, they're held together by intermolecular forces. If you've forgotten about IMFs, worry not. We are definitely going to be reviewing those later in this unit. Now, covalent compounds typically do not conduct an electric current because they don't have mobile charges. They don't have charges at all. Unless you have a strong acid. Strong acids, of course, will dissociate into charged particles, which is why strong acids are great electrolytes when dissolved in solution. Now, Coulomb's law. Everything comes back to Coulomb's law. Well, Coulomb's law tells us that the negative electrons of one atom and the positive nucleus of the other atom are attracting each other. But the two nuclei involved in this bond will repel each other, like charges repel. So finding the optimum bond length is a balance between these attractive and repulsive forces. The bond length will occur at the lowest potential energy, where there's the maximum attraction and the minimum repulsion. So you'll often see this as a graph. So the internuclear distance, of course, is just the distance between the two nuclei in the bond. So at the lowest potential energy, that's the measured bond length. Any closer, and they'll start repulsing each other, but if they're far apart, then the attractive forces aren't being maximized. Okay, we can talk about something called bond order, which just tells you the number of chemical bonds between a pair of atoms. It's just another way of talking about single, double, and triple bonds. Single bond, of course, is a bond order of 1. Now, single bonds are the weakest of the 3 bond types, and they are the longest because they have the minimum number of electrons between them. Double bonds are in the middle, and triple bonds are going to be shorter and stronger. When you have multiple bonds, like double or triple bonds, well, of course, you have more electrons between the two nuclei. So that decreases the repulsion. There's basically the shielding, all those delicious electrons. So since the repulsion between the two nuclei is being decreased and the added electrons increases the attraction between the nuclei and electron density, therefore these are multiple bonds, double and triple bonds, are going to have a greater bond strength, and the nuclei can get closer together, so it will decrease the bond length. Okay, so let's take a look at a couple of simple covalent bonding molecules. Let's start with showing how 2 fluorines would bond. First, let's look at 2 single atoms of fluorine. Fluorine, of course, is a halogen. Thus, it has 7 valence electrons, 3 of which are all paired, but 1 is unpaired. It is the unpaired electrons that participate in covalent bonding. So in this case, these 2 single electrons from the 2 fluorine are going to hook up and form a single bond. The most common way to represent a single bond, at least in America, is drawing a line, which represents the 2 electrons being shared. However, in Europe and some other places, you will actually find it drawn, instead of a line, it's with 2 dots, which makes sense, right? Because it's showing 2 electrons being shared between them. Sometimes you will also see the lone pairs, instead of being dots, being drawn with lines. Now, I'm going to strongly encourage you to stick to this one because this is the most common one and this is the one I'll be using. However, I just want you to be aware the other 2 things exist, just in case you see a problem with them. It's totally a thing. Okay, so that's a fluorine to fluorine single bond. Let's look at what happens when 2 oxygens bond. Oxygen, of course, has 6 valence electrons, which means it has 2 single unpaired electrons, which is why when 2 oxygens bond, they will actually share 4 electrons between them in a double bond. This, of course, can also be represented with dots. I always thought that looked cool. Okay, last but not least, delicious nitrogen. Nitrogen, of course, 5 valence electrons means 3 unpaired electrons. So when nitrogen to nitrogen hooks up, you are getting a triple bond with 6 shared electrons. This bond is super stable. This is just like ridiculous. The nitrogen to nitrogen bond, it took chemists forever to figure out how to break it. And when they finally did, they were able to turn it into ammonia and use it for fertilizer and revolutionize farming. Go chemistry, go. Of course, this bond can also be represented with dots. And in fact, I've actually seen it represented 2 different ways with all the dots. So yeah, the lines just take so much less time, but in case you see the dots somewhere, you need to be able to recognize them. Okay, couple of quick practice problems. So, first you're going to explain why would it require more energy to break the bond between O2 than F2? And then you're going to rank. Put in order of increasing bond length. You're looking at oxygen, fluorine, nitrogen, and hydrogen gases. All right, so try both of these, and when you are ready to check your glorious answers, unpause the video. Well, for the first one, it's recognizing that, of course, O2 has a double bond. Sharing 4 electrons, stronger attraction, is going to take more energy to break than the single bond in F2. Okay, so for number 2, let's do the easy ones first. Hopefully you recognize that nitrogen, that triple bond, is going to be super short, which means the double bond of oxygen is going to be a little bit bigger. And so, of course, the single bond of fluorine is going to be the biggest of all. But wait, what about hydrogen? Well, hydrogen is super tiny. So it is a single bond, but it's only got 1 energy level. So a hydrogen to hydrogen bond is actually shorter than everybody else, even the nitrogen-nitrogen bond. Okay, we will totally talk more about covalent Lewis dot structures, but that won't be until the next video for the next day. Instead, let's talk about these glorious, crazy things that are called network covalent solids. Most of the time, when different molecules are held together, they're held together just by intermolecular forces. Each molecule is a discrete thing. But a network covalent solid is a magical substance, which is actually a crystal. But the crystal, instead of being held by ionic bonds, is formed by covalent bonds. And this is just super crazy strong. So if you have a perfect single crystal of a network covalent solid, you have a single giant molecule. So these things are very rigid and hard because those bonds, everything's fixed in place in 3 dimensions, and they have very high melting and boiling points. They also tend to be very stable and thus chemically inert. They're not reactive, they don't really dissolve in water. Diamond is the most famous example of this, and diamond is the hardest substance on Earth. In fact, if you want to test the hardness of something else, determine what it is, you take a diamond and you scratch it, and that's how they test the hardness, because diamond, as a covalent network solid, is the hardest substance on Earth. Now, graphite, not as hard. It is still a network covalent solid, but notice graphite is only 2-dimensionally bonded in sheets, whereas diamond, of course, is 3-dimensionally bonded. So that's why graphite is perfect for pencils, right? Because the layers are shearing off as you write, but it's still maintaining its composition in the 2 dimensions. So let's compare the different types of crystalline solids we've seen. So of course, the network covalent solids are the ones that are held together by covalent bonds in 3 dimensions, or 2 dimensions, but basically covalent bonds. Ionic solids, like tasty table salt, sodium chloride, are of course they're crystals made up of cations and anions. So they are of course held together by ionic bonds. Now molecular solids, this is what we call things that are covalent compounds that aren't 3D covalent or 2D, but they're just molecules. So hence molecular solids. So sugar, delicious, is a molecule. So protein crystals, sucrose, glucose, all those delicious things, they are held together, but they're held together by intermolecular forces, which are the attractive forces between separate molecules. Okay, We are going to skip forward. There's a couple pages of practice we're going to do in class, but we are going to skip to page 12 and talk about the difference between polar and nonpolar covalent bonding. Yum! I'm sure you remember our discussions of electronegativity from all of our fun and exciting periodic trends. Well, remember, electronegativity is just the attraction or pull on the bonded electron pair, and this determines individual bond polarity. Now, a nonpolar covalent bond is what you call it when the bonding electrons are being shared equally. This only happens when you've got a very small electronegativity difference. Now, electronegativity is measured in a unit called a Pauling, but oddly enough, it's a unit, but it doesn't have a unit attached, a number, I guess. But, so basically, these measures of electronegativity are in Paulings, and if you subtract the electronegativities of two atoms, if your number is less than 0.4, it doesn't really look like a 0.4, that's when things are considered equal enough that it's equally shared. So, any diatomic molecule, of course, is going to be nonpolar, because, like, if you've got a chlorine and a chlorine, look at that equal electron density sharing. Of course, each chlorine has the exact same electronegativity, so they have no choice but to share equally. Now, the important one that you absolutely have to remember is hydrocarbons. Hydrogen and carbon don't have the exact same electronegativity, but it's close enough. So you are expected to recognize that any hydrocarbon things with just carbon and hydrogen are considered nonpolar. Okay, well that means things that are polar must be things that have a different electronegativity and thus an unequal attraction for your shared electrons. So their difference in electronegativity is going to fall between 0.4 and 1.9. Well, 1.9 or 2, it kind of changes depending on the source. So the atom that has a greater electronegativity has a greater attraction for the shared electrons, so it will have a greater amount of electron density. So this unbalanced electron cloud, the uneven electron density, creates what's called a dipole or a dipole moment. This means there's going to be a partial negative charge on the atom with a higher electron density and a partial positive charge on the atom with lower electron density. And we use an arrow to represent the dipole moment. The arrow is going to point towards the more negative pole, the more electronegative atom, and it has a cross tail, which kind of looks like a plus sign, at the positive pole, which is where the least electronegative atom is. So if you are looking at hydrofluoric acid or hydrochloric acid, of course, fluorine and chlorine are going to be way more electronegative. So that means when you're looking at their electron density, there's going to be such a greater crowd of electron density around the more electronegative atom. Look at hydrochloric acid. Chlorine is stealing all the electrons and poor little hydrogen barely has any. That's what creates the dipole. Remember that we use a lowercase delta to show that there is a partial, so that's partial negative on the side of the atom that has the greatest electron density, and a partial positive on the side with lowest electron density. So that, of course, leads to all sorts of fun and exciting things. We will get to that shortly. But first, let's talk about ionic bonds. An ionic bond is where the electronegativity difference is so great that one atom basically takes all the electrons for themselves. So if you look at something that's considered a purely covalent bond, that's where you have the equal sharing, very low electronegativity difference. All the way to an ionic bond where there is no sharing at all. Gasp, the horror. And of course, a polar covalent is somewhere in between. It's important to recognize that almost all chemical bonds aren't purely one or the other. They're just somewhere between ionic and covalent. There is mixture. All right, you now know everything you need about ionic, metallic, and covalent bonding, at least for today. So you are all done with your notes, and we will practice all of these glorious things in class. I'll see you there.